Okay, we're now recording. And share the screen. All right, just a quick word about the exam. So you should have gotten an email back from me about your exam and your midterm score. If you missed the exam, remember you get to drop one exam, but only one exam gets to be dropped. Okay, which actually could be part of the final exam. You don't get to drop the entire final exam, but if the final exam turns out to be worse, you get to drop part of it as part of the dropping procedure, as it were. Okay. All right, so I'm done with that. If you have any questions about that, let me know. But you should have your exam back. I sent on Friday or Saturday the solutions, so you've got the solutions there. I messed up the first time, but you know, what else is new? And so we're on to moving on. So this is my new adjusted calendar. So last Tuesday, 3/16, I was in with 15.2. Okay, so my goal is 15.3, 4, and 5 this week. Okay, so today 15.3 and 4, hopefully. Next time 15.4 and 5. And I was going to give you a quiz on Thursday on 15.3, which is on polar coordinates, areas using polar coordinates. Okay, then we have a week off. Okay, I'm not quite sure about the date of the next exam. In case you're wondering, you might think we're way ahead. We're actually not that far ahead. If I notice 15.4 and 15.5, that matches right over here. Okay, so again, it seems like we're 2 days ahead, but remember, I had to gain a day over here. So in the grand scheme of things, it looks to me like we're actually just 1 day ahead. Okay, so if this thing were to land right there, then I'm exactly where I wanted to be, which is 1 day ahead of this original schedule, where you know the last exam would have been on 5/18, but now we're aiming for 5/13 for the last exam. So it looks like we're 1 day ahead. Okay, so I'll do 15.3 and maybe some of 15.4 today, and then 15.4, 15.5. So when it's the next exam, I'm not sure exactly. I very well may keep it on Thursday the 22nd. I seem to think that Thursday exams are better than Tuesdays. I mean, it gives me the whole weekend to grade it as opposed to, you know, 2 days. Okay, so what I might just go ahead and do like last time is give you exam 4 here. And if I happen to get started with our last chapter, chapter 16, then so be it, but leave it here. So I guess we'll just say I'm leaning toward, if there's such a thing, I'm leaning toward keeping exam 4 on this day. And if I move everything up like here, then I may have actually gotten started with chapter 16 ahead of time. But I'm very much leaning toward keeping this date for exam 4. But again, for exam 5, the goal is having it on Thursday, 5/13. That way we can have 1 day for review questions and answers, and then have the final exam. And then we're done with the class. Is that right? So that's that. Okay, anybody who joined late, go ahead and put your name in the chat and I'll get you later. Okay, so I think we're good. All right, so we're here, 15.3, 1 to 31 odd, except skip 17 and 27. 15.4, now 15.4, there's only 4 questions. I say only 4. It's because some of these problems are really, really long. I mean, really long. Okay, and to do more problems would, frankly, almost be torture, in my opinion. Okay, and there's a lot of physics applications to it. Okay, now I'm not a physics instructor. I know a little bit of physics. I took physics classes and so on, but there's some physics context to this, and we're just going to barely scratch the surface of it. Okay. All right, so let's go to 15.3. Now you should have had some exposure to polar coordinates already, hopefully in Calc 2. Those of you that had me for Calc 2, we did polar coordinates. So 15.3, double integrals in polar coordinates, page 1010. Okay, suppose we want to integrate over a region like this. Okay, it can get kind of clumsy, even if it's a unit circle. X squared plus y squared equals 1. Well, if I go upper and lower, this would have to be y equals square root of 1 minus x squared. This would be negative of radical 1 minus x squared. What if I want to integrate over a region like this? Okay. So instead, we switch over to polar coordinates. Okay. Now, I will make an assumption that you've all had some polar coordinates, and perhaps if you've never had polar coordinates, let me know or put it in the chat or send me an email. But you should have had some exposure to polar coordinates in the past. See, I don't remember too much about it. You don't need to. I'll give you all the formulas that you need on polar coordinates, but a very quickie review of what you need to know for polar coordinates. So any point in the XY plane, let's say this point over here, okay, we know how to do X and Y. You go this way for X, and you go this way for Y. Okay, but instead of X comma Y, you could also have R comma theta, where R is a distance away from the origin, and theta is the angle in standard position, right? So if you say theta is pi over 6, and you walk out 3 units, that specifies a point. Okay, and you can see from the picture, there are certain relationships that we have. We obviously have the Pythagorean relation, x squared plus y squared equals r squared. Okay, and we also have from trig that x is equal to r cosine theta, y is equal to r sine theta. From this picture, cosine of theta is adjacent over hypotenuse. Cosine of theta is x over r. Multiply both sides by r, you get that. Okay, sine of theta is opposite over hypotenuse, so that would be y over r. Again, multiply both sides by r, and you get that. Okay, so you want to put this on your next cheat sheet, your formula sheet for equations involving polar coordinates. R squared is equal to x squared plus y squared, and x equals r cosine theta, y equals r sine theta. Okay, then we're going to have something called a polar rectangle, which is not a true rectangle, but it's very close to a true rectangle if delta theta and delta r are small, so to speak. So let me show you the picture on page 1011. What's happening here for a tiny change in area. Okay, so here's the region that we may be integrating over. Okay, so instead of x going this way and y going this way, which we're comfortable with, okay, r is going from one number to another number. They call it a and b. So this is a radius. Let's say this is 1. This radius is 3. So the radius is going from 1 to 3, and theta is going from alpha to beta, right? So your angle is going from here, maybe it's 30 degrees out to 60 degrees, right? So the picture's like this. All right, so in rectangular coordinates, I won't turn back to it, but it's very straightforward. You can do a chop with delta x in the delta x direction, and you can chop this way in the y direction, right? So chop, 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 chop. So your tiny little rectangles have a tiny delta x and a delta y. Well, in polar coordinates, the chops are like so. So in this picture, the delta r is split into 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces or whatever. And this is delta theta. Delta theta is 1, 2, 3, 4, 5, 6, 7, 8 pieces. So they chop this way. Okay. So imagine your delta r's, they're still going to be curved, right? Curve, 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 curve. And imagine delta theta, you're starting here, and it's too big. Use this. So chop, chop, chop. We're moving along like so. It ends up looking like this. Okay. So we have something here called a polar rectangle. Okay. Now, if you look at this big picture area, you say that doesn't look like a rectangle. But look at this one. It looks more and more rectangular-ish, right? It looks more and more like base times height. Okay. So you go chop, 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 chop into these. Okay. Take a look at any one of these very small ones. It's kind of like a rectangle, right? If you look at that one, okay, that's kind of a rectangle. That's kind of a rectangle. Now you might argue, well, it's still curved. You're right, it is curved. But remember, the game is let delta theta approach 0, let delta r approach 0 in the Riemann sum, right? You end up with a limit. So chop this up. Suppose delta theta is chopped up into a million pieces, right? And delta r chop up into a million pieces. You got a very, very, very tiny one of these, which looks more and more and more rectangular-ish, right? So in the limit, you're just adding all of these up. So how do I find the area of one of these so-called fake rectangles? Technically, it's a polar rectangle. But again, if we chop it very finely, it looks more and more like a true rectangle. Okay, I don't know. But only analogy I can think of is maybe you have a piece of meat or a piece of lettuce. You ever take something like this, and it doesn't look like a rectangle, but if you do chops, right? Just do the chop, 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 chop this way. I mean, literally get a knife and do it, and then chop, chop, chop this way. Then you got real tiny pieces. Each one of those looks rectangular, doesn't it? Even though the original didn't, but after you're doing the chop, 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 chop this direction and chop, chop, chop this direction, right? You got your tiny little pieces of onion or lettuce or meat or whatever, and they look like they're rectangles when you chop it up in a whole bunch of pieces. Okay, so all I have to do is find the area of one of these. That leads us to this picture. Okay, dA, tiny change in area, length times width. Okay, this distance is delta r. In the limit, it's dr. Okay, this, however, is not just d theta. As a distance, it's r d theta. Do you remember in trig, the formula for arc length, S is equal to r theta? Okay, so if you go all the way around a circle, right, and you wanted to find an arc length, the formula for the arc length, this little arc, S is r theta. So delta S would be r d theta. Okay, in short, this is dr, this is r d theta, which means dA is equal to r d theta dr, but we usually say r dr d theta. All right, bottom line, you might be saying, I have absolutely no idea what you're talking about. Okay, just tell me what to do. Okay, so here's what we have. Okay, so to change to polar coordinates, and when would I want to change to polar coordinates? In rectangular coordinates, it would be too difficult to integrate over something like this or this. But in polar coordinates, you can kind of see the circular region, right? You see the circle, okay, a radius from here to here, maybe that's from 1 to 2. Okay, and theta goes from one number to another number. Okay, so the double integral is f of x, y, dA. You change x to r cosine theta, change y to r sine theta, and then change dA to r dr d theta. Okay, and then r goes from A to B, theta goes from alpha to beta. Okay, and you can put this on your next cheat sheet if you wish. Okay, so again, if you didn't understand my explanation here, that's okay. Just let me know how to do the problems. This is how you do the problems. Okay, so if you see x, change it to r cosine theta, y, change it to r sine theta, and then dA is going to be r dr d theta. And that's basically what's happening. All right, so that's what we got. Let me check one thing quickly in the chat. Okay. All right. So yeah, anybody that joined late, put it in the chat and I'll get a little bit later. All right. So again, bottom line, you didn't understand my explanations or whatever. What do you need for this section 15.3? Okay. Definitely put this. X squared plus y squared equals r squared. X is r cosine theta. Y equals r sine theta. Okay. So for a lot of these problems, they give it to us in x and y. Change x to r cosine theta, change y to r sine theta, and then dA is r dr d theta. Okay. All right, so I think we're ready to do some problems. And a quick double check of what we have here. Again, we're supposed to do, whoops. Just 1 to 31, except skip 17 and 27. Okay, so again, I'll show those to you. For those of you that don't have the book. 7, 11, and 13, 15. And there's some more there. Some more there. And there. Okay, and we had to go to 31, was it? Yeah. Check what I got here. Yeah. All right. So here we go. All right, now before we start, so one thing I want to say is to find the area of something, it's the double integral of 1 dA, or just double integral of dA. That gives you the total area. Okay. It's just like the length of an interval, okay? Integral dx gives you the length of the interval in 1 dimension. Okay, so the double integral of dA gives you the area. And as you might guess, triple integral of dV gives you the volume. Okay, so dA now has 3 forms. dA can be dy dx. So if you have a tiny little rectangle, you can go dy first and then dx, or switch it around, you can have dx dy. But in polar coordinates, you now have r dr d theta. So one thing to watch out for, sometimes students will forget to put the extra r there. Okay, in polar coordinates, the dA, little change in area, is r dr d theta. You have to remember to put the r dr d theta. Okay. All right. So question 5, sketch the region whose area is given by the integral and evaluate the integral. So number 5, okay, see this r dr d theta? When I'm integrating that, I'm finding the area. Okay, that's just like saying 1 dx dy. If I integrate 1 dx dy, you're finding area. So r dr d theta is also area. So r is going from 1 to 2, theta is going from pi over 4 to 3 pi over 4. So here's the region in question. Okay, so the integral r is going from, well, yeah, from 1 to 2. Okay, so here's 1, here's 2, here's pi over 4, here's 3 pi over 4. So when I integrate, I'm finding this area. And notice that's going to be quite difficult to do in rectangular coordinates, in normal x and y, right? We didn't have any weird shapes like this, but in polar coordinates, it's fairly straightforward. So I'll just integrate r dr d theta and go from there. And a quick word, for a lot of these kind of problems, if it doesn't involve theta, you can just pull it out as the length of the interval. Okay, so for this one, there's no theta. You could just immediately go to saying 3 pi over 4 minus pi over 4, which is pi over 2, times the integral of r dr. Okay, that would qualify as so-called length of the interval. Okay. All right, so let's go to problem 9 now. Okay, evaluate the given integral by changing the polar coordinates. Double integral of sine of x squared plus y squared dA. R is the region in the first quadrant between the circles with center of the origin and radii of 1 and 3. Okay. So here's the thing we're integrating. Here's the region. Radius of 1, radius of 3, first quadrant. Okay, so R goes from 1 to 3, theta goes from 0 to pi over 2. Okay, again, notice how difficult that integral would be in x and y. It's very messy, but in polar coordinates, it's quite nice. Okay, so I change x squared plus y squared to r squared times r dr d theta. Theta going from 0 to pi over 2. R going from 1 to 3. Actually, I got these backwards. Sorry, I should have reversed it. But fortunately, in this case, it doesn't really matter, because this is what I'm talking about from what I said before. Yeah, these should technically be reversed. Okay, this expression does not involve theta, right? This is all constant d theta. So I just take out the length of the interval. So how far is it from 0 to pi over 2? Pi over 2. So just take out the pi over 2, and I'm integrating sine of r squared, r dr d theta. Okay, this is going to be a u substitution, right? Let u equal r squared. du is 2r dr. I need a 2 inside, which means I put an extra half outside. So yes, if I did a u substitution, it'd be sine of u. But we're doing so many integrals, it's a lot faster to just say, don't do the substitution, just go straight to it. What's the integral of sine? Negative cosine. So negative pi over 4 cosine of r squared from 1 to 3. Okay, and you might recall, if I have a negative here, I can make it a positive and switch these two around, which is actually preferred in this case. Okay, so pi over 4 cosine 1 minus cosine 9. And you can leave your answer like that. That's pretty much it. Right, so that's my answer for that one. Okay, 13 says double integral over the region of arctan y over x dA. That looks really weird, but it's actually going to be quite nice overall, as we shall see. 1 less than or equal to x squared plus y squared less than or equal to 4. 0 less than or equal to y less than or equal to x. Okay, if they give it to me like this, if this says equal, right? 1 equals that, what's the radius? 1. How about x squared plus y squared equals 4? What's the radius? 2. So for the radius, I'm integrating from 1 to 2. Okay, we know what y equals 0 is like. Y equals x is like so. So here's y equals 0, y equals x. So what is my theta going from? Here to here. So what is this angle? 0. And what is this angle in radians? Pi over 4. Now, how do I deal with this weird function? Okay. They didn't put it in the problem. But look back at this picture. Didn't write it down. You probably saw it in Calc 2, though. What is the tangent of theta? Tangent is opposite over adjacent, right? Tangent of theta is y over x. Give me a statement involving inverse tangent. If tangent of theta is y over x, inverse tangent of y over x is theta, right? That's the way inverse functions work, right? For inverse functions, you just switch the x and the y, right? Just move that over there, move that over there. Inverse tangent of y over x is equal to theta. Okay. In other words, it's kind of sneaky. This is theta. Okay, so tangent of theta that I showed you is y over x. That means theta is arctan y over x. So what do? Change this to theta. And then dA is r dr d theta, right? dA can be either dy dx or dx dy. We've already seen that. Or r dr d theta. Okay, in a little while, we're going to do dv, little change in v. You've got a dx, dy, and a dz in some order, which could also be dz, dx, dy, or dy, dx, dz, right? And there's going to be more on top of that also. Okay. So again, the area is a double integral of dA. The volume is going to be the triple integral of dv. Okay. Yeah, I'll squeeze this in. In one dimension, arc length is a single integral of dx. Length of the interval, talked about that. Okay, it'd just be b minus a, one dimensional. Integral of 1 dx gives me the length of the interval. 2 dimensions, area is double integral of dA. Triple integral, the volume is a triple integral of dV. All right, so what do I have now? I have theta, and then dA, which is r dr d theta. R going from 1 to 2, theta going from 0 to pi over 4. Okay, then I got it. So integrate with respect to r, that means theta is constant. So r squared over 2 theta, r going from 1 to 2. Okay, plug in 2, I get 2. theta. Plug in 1, I get a half. So 2 minus a half, 3 halves. Take out the 3 halves. Then I integrate from 0 to pi over 4, theta d theta. And now it's easy. So 3 halves, theta squared over 2 from 0 to pi over 4. Plug in 0, you get 0. 3 over 2 times 2 is 3/4. Plug in pi over 4. Pi over 4 squared is pi squared over 16. So 3 over 4 times pi squared over 16, 3 pi squared over 64 is my answer. All right, that takes care of that. Okay, now 15 is a little bit harder, but that is something you maybe saw in Calc 2. Those of you that took me, I know we had it. Use a double integral to find the area of the region. One loop of the rows r equals cosine 3 theta. Okay, so we have to do a real quickie graph of one loop of r equals cosine 3 theta. You don't have to get polar graph paper for this, but I just made a real quick chart here and said, okay, when do we come back into the pole? And by the way, the origin is sometimes called the pole in polar coordinates. Okay, so I need to get one loop. So I plug in 0, I get 1. That's over here. Then I thought to myself, how can I make this expression 0? Okay, I know the cosine of pi over 2 is 0, but it's 3 theta. So I'm tripling the angle. I want to divide pi over 2 by 3, which is pi over 6. In other words, if I plug in pi over 6, I'm taking the cosine of 3 pi over 6 or pi over 2, and I get 0. Okay, so that tells me I'm coming into the pole, the origin. And that also led me to show that, well, if I plug in negative pi over 6, that's also 0, because then I'll be taking the cosine of negative pi over 2, that's also 0. So here is one loop. Okay, so this is negative pi over 6, this is pi over 6, one loop. Okay, so to find the area is always a double integral of dA, which in polar coordinates is r dr d theta. Okay, now I could integrate from negative pi over 6 to pi over 6. I'd rather not. I'd rather integrate from 0 to pi over 6 and multiply by 2. Now you can only do that if you have the symmetry. In this case, you definitely have symmetry. Okay, and some of you saw this in polar coordinates. Some of you had me last semester that, there's another loop over here and another loop over here. Real nice pictures, but anyway, we just care about the area here. Okay, so I'm going to take 2 times the integral from 0 to pi over 6. Okay, so r is going from 0 to the function. Okay, so again, think of your slices going like that and like that and like that. It's not a constant. Okay, so it's going from 0 to the function. The function is cosine 3 theta. And theta goes from 0 to pi over 6. Okay, and what am I integrating? R dr d theta. Okay, since this one involves theta, I can't just quickly do the trick that I did before. So, this doesn't have any theta. Yeah, but after I integrate, it is going to have theta from here. So I can't just use the trick of taking out pi over 6 minus 0. Okay, so you have to wait. All right, so integral of r is r squared over 2. And r is going from 0 to cosine 3 theta. 2's very conveniently cancel out. Plug in 0, you get 0. Plug in 3 theta. I'm now integrating cosine squared of 3 theta from 0 to pi over 2. Okay, cosine squared of 3 theta. Okay, you might recall doing something this in Calc 2. That can be changed to 1 plus cosine of twice the angle divided by 2. Maybe I'll write the identity here. Cosine squared theta is 1 plus cosine 2 theta over 2. cosine squared theta is equal to 1, that's a 1, plus cosine 2 theta over 2. So I double this angle. So to double 3 theta, you have 6 theta. And instead of dividing by 2, I decided to multiply by half and put it outside. Okay. So I now have 1/2 integral from 0 to pi over 6 of 1 plus cosine 6 theta d theta. Okay, so now I'm ready to integrate. Keep the half there. Integral of 1 d theta is theta. Integral of cosine 6 theta is sine of 6 theta times 1/6. Again, you should get comfortable over here by not doing an actual U substitution. Just think of doing the chain rule in reverse from what you did in calculus. Okay, if you were to take a derivative of this by the chain rule, you would multiply by 6, right? So when you integrate, you divide by 6 or multiply by 1/6. So, and as you can see, I did it so well, I messed up again. So 1/2 integral of 1 is theta. Integral of cosine 6 theta is sine of 6 theta times 1/6. That should be a 1/6 there. From 0 to pi over 6. And again, to double check, take the derivative. Derivative theta is 1. Derivative 1/6 sine of 6 theta is 1/6 cosine 6 theta times 6. That 6 cancels to 1/6, and I have 1 and 1. So you know it works. Okay. And again, you know, whenever you see shortcuts, do it. Is it true when I plug in 0, I get 0? That's 0. Sine of 0 is 0. Yes. So don't even bother with it. Just plug in pi over 6. Okay. If you plug in pi over 6 here, 6 times pi over 6 is pi. Sine of pi is 0. So I just put pi over 6 here. And some of you might recall in Calc 2, that happened a lot when you're doing stuff like this. Okay, the 0 came out to be 0, and even this expression came out to be 0. So the only thing of substance is this. So 1/2 of pi over 6, my answer is pi over 12. Okay, I started to do 17, then I figured out I don't want to do that after a while, so skip that. I think I said skip 17, didn't I? Let's see, skip 17 somewhere. Yeah, skip 17. All right. Okay, then 21 should use polar coordinates to find the volume of the given solid. Okay, so volume is a double integral of Z in general. Okay, so quick little timeout. Area was integral from A to B of f of x dx in Calc 1. You're basically integrating y, right, to find area under a curve in Calc 1. So volume is a double integral of Z. You're in xy plane and you have some Z function up here. Okay, so if it asks for the volume, you're integrating Z in general. So volume is a double integral over a region of Z dA, which is double integral of f of xy dA over a region. Okay, so this is a 3-dimensional analogy of what you did in Calc 1, right? In Calc 1 and 2, we did the integral from A to B of f of x dx. The picture was like this. You're integrating y. What is y? The heights, right? So on a real deeper scale, you were doing chop, 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 right? Get a Riemann sum, add this up, add this up, add this up, okay? And you're getting an approximation by taking the sum of the areas of all these rectangles, right? So you're integrating the height. So likewise, to find volume, you're doing a double integral of Z. The Z's are the heights. In X and Y, you go chop, 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 chop this way, chop, chop, chop this way, get a height, get a height, get a height, add them all up, you get the volume, right? And again, I'm using volume, meaning the functions above. We know, what happens when it's below the floor. That's just like over here, right? At the beginning, you had all the functions above, but then later it was below, then that was represented by a negative. So likewise here, okay? But if the function was always positive, it was the area. So likewise here, for f of xy being Z, if the function's always positive, then you are getting a volume. Okay, so volume is a double integral of z dA, or f of xy dA. Okay. All right, so 21. Okay, so below the plane 2x plus y plus z equals 4, and above the disk x squared plus y squared less than or equal to 1. Okay, that's the unit circle, isn't it? The unit circle and the interior. Okay, so you have a plane. Okay, imagine you have a circle. Okay, let's pretend it's this circle. You have a plane, maybe represented by a piece of paper. Okay, it's crooked. Okay, imagine that piece of paper in a plane only above this. Okay, and it's again some crooked plane. You're going to get some kind of volume. Okay, what is that volume? Right? So first thing I'm going to do is make it in terms of z. Z is 4 minus 2x minus y. So I am doing the double integral of z dA. So z, 4 minus 2x minus y. This is z, and this is dA. Again, just like in Calc 1, you're integrating the height, y dx. I can't show it to you in 3D, but it's the same concept. Okay, you have this surface above, and you're trying to find a volume. So you're integrating z dA. In polar coordinates, dA was r dr d theta, and 4 minus 2x minus y, change x to r cosine theta, change y to r sine theta. It said unit circle. R goes from 0 to 1, theta goes from 0 to 2 pi. All right, so there we go. Distribute the r, 4r minus 2r squared cosine theta minus r squared sine theta dr d theta. Okay, integrate with respect to r, which means theta is constant. So 4r, 2r squared. Yeah, you definitely want to get some proficiency in doing this pretty quickly, but you shouldn't have to go 4r squared over 2. You know, okay, 2r squared. 2r squared, 2r cubed over 3 cosine theta minus r cubed over 3 sine theta. R is going from 0 to 1. Is it true when you plug in 0 for all the r's, you get 0? 0, 0, 0, yes. Just plug in 1. 2 minus 2/3 cosine theta minus 1/3 sine theta d theta. Okay, now I could integrate this. I'm trying to convince you that these two are automatically 0. Okay, when you integrate from 0 to 2 pi of either cosine of sine, you get 0. Right? That was a sine function, right? You're going from 0 to 2 pi. By symmetry, just as much above as below. So the integral will be 0. Right? You could integrate it. It'd be what? Negative cosine x and then plug in. It's 0. Likewise for cosine, one period looks like this, right? Again, by symmetry, this is also 0. Integral from 0 to 2 pi of cosine x dx is also 0. If you're not convinced of that, I can do this quickly. Integral of cosine is a sine, right? Sine x, plug in 2 pi, 0. Plug in 0, 0, 0 minus 0 is 0. For this one, integral of sine is negative cosine. Okay, plug in 2 pi, you get 1. Plug in 0, you get 1. So the opposite of 1 minus 1 is 0. Okay. In a nutshell, I can immediately call each of these 0. See, what about the 2/3? It doesn't matter. It's negative 2/3 times 0. Okay, so just integrating 2. Integral of 2 d theta is 2 times the length of the interval for pi. Right? So we're trying to do some shortcuts, obviously, from all this. Okay, 25, you can see I messed up the first time I did it, but you know, there we go. Okay, so I think I finally got it over here. So yeah. Now I'm not really sure, but I might actually be, you know, one of the teachers or the teacher that makes the most mistakes in a math class. I don't know. But be that as it may, I'll keep going until they fire me, I guess. But you all know I make lots and lots of mistakes. Okay, so 25. Looks a little bit weird. Okay, maybe I'll just do the setup, then we'll break, and then I'll do it afterwards. It's just getting to be close to 7. Above the cone, why is it blinking back and forth yellow there? Go like that, that should do it. Okay, z equals square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals 1. Okay, how do I do something like that? So I'll show you part of the picture. The actual work for it's going to be a little bit messy, so I'll save it until after the break. Z equals square root of x squared plus y squared, which by the way is equal to r. X squared plus y squared is r squared, right? Whose square root is r. So it's x squared plus y squared equals z squared. Okay, now one way you can think of this is suppose z is 1. You have a unit circle. Suppose z is 2. You have x squared plus y squared equals 4. Suppose you have z is 3. X squared plus y squared equals 9. So as you go higher and higher up, you get circles going further and further out. Okay, so you end up with a conical structure like this. Okay, so this is the origin. Okay, and it says below the unit sphere, x squared plus y squared plus z squared equals 1. Okay, which looks like this. In polar coordinates, what's x squared plus y squared plus z squared equals 1? Well, z is the square root of 1 minus parentheses x squared plus y squared. And the reason why I write it like that is because I can make it as radical 1 minus r squared. So we're trying to find the volume of this thing, which almost does look exactly like what we normally think of as an ice cream cone. Okay, but it's the full volume. Okay, so here's the conical part. Okay, and the scoop of ice cream is kind of like that, but it's the whole thing, including dug all the way down. Okay, so I'm trying to find the volume of the whole thing, not just this part over here. Okay, so when you buy I'm digressing, but when you buy an ice cream cone, right, in some sense, you're almost being cheated because, you know, they place the ice cream right here, but unless they're very nice, they don't pack it in, right? They don't shove in all the ice cream there, so you end up with more ice cream, and you can't see it. Okay, unless they're very nice and say just, you know, shove it down. They usually don't do that because you can't see it. So they say, oh, you can't see it. Whether I shove it down or not, it looks the same when they give it to you, right? They give you the ice cream cone. You see this, you don't see anything shoved down. So they say, well, you can't see it anyway. It looks the same. So why should I give you more ice cream, right? Okay. And then, I don't know, maybe you or I also, you take that and you kind of shove it down yourselves. You ever do that? Okay, you kind of use your tongue and shove the ice cream further down into that, I guess. Maybe it's starting to melt, so you want to make sure it's there. But normally when they give you the ice cream, it's just on top here, right? They don't shove it down. But for this particular problem, when we're giving the volume, it's including the cone part. So pretend they actually did shove down the ice cream, which I don't think, you know, any ice cream store does, okay? And the top part. We're trying to find the volume of that whole thing. Okay. This actually falls in the category of upper minus lower. Remember at the beginning of Calc 2? Okay. At the beginning of Calc 2, you were doing stuff like this, right? So what's the area between the two curves? What was the integral of f of x minus g of x? That's the same thing over here. I do have to figure out the region in the xy plane here, but in this case, the upper function is this, and the lower function is the conical part, the three-dimensional analogy of what you have over here. Upper minus lower, upper y, lower y. So upper z is the sphere, and the lower z is the cone. Okay, so we'll look at that after the break. So it's almost 7. So let's go ahead and break until roughly 7:10, I guess, as normal. Okay, so let's break until roughly 7:10. Anybody who showed up late, please put it in the chat, and I'll get you eventually. Okay, all right, great. All right, folks, I'm going to pick up where we left off. All right, so we said we need to find the upper and the lower. I need to find out the corresponding region right here in the XY plane that I'm integrating over. To do that, I need to find out where these two graphs touch. In other words, where does this touch this? Well, since x squared plus y squared equals z squared here, if I replace x squared plus y squared right there with z squared, okay, I have x squared plus y squared plus z squared, x squared plus y squared equals 1. Okay, I'm trying to find out where they touch. So I set them equal. Okay, since x squared plus y squared is z squared, yeah, sorry, I'm going to put x squared plus y squared there. So I have x squared plus y squared plus z squared. This is z squared equals 1. That's 2x squared plus 2y squared equals 1. Or x squared plus y squared equals a half. That's a circle center of the origin with a radius of the square root of a half, or radical 2 over 2. So the region that I'm integrating over is a circle center of the origin with a radius of radical 2. Okay, so if you imagine this region. So to find the volume between the cone and the sphere. So if I integrate the entire sphere, I'm getting this. Okay, but I'm throwing out, okay, well, I'm not really throwing out the cone, I'm throwing out the part below the cone, and I'm really throwing out the anti-cone, if I can coin such a word. Okay, we think of the inside, but it's the outside. Okay, so underneath is the cone. So I'm trying to say it's like this, upper minus the lower. So the upper is the spherical part. The lower that I'm throwing out isn't the cone. I'm keeping the cone. I'm throwing out the anti-cone, right? What's the anti-cone? It's the part within the cylinder of this x squared plus y squared equals 1/2. And if I go straight up until I touch the cone, I'm throwing everything out besides the cone. So I'm throwing out the anti-cone, so to speak. All right, so here we go. So integral r goes from 0 to radical 2 over 2. Theta goes from 0 to 2 pi all the way around. Upper radical 1 minus r squared minus the lower, which is r. Okay, so remember the sphere, you can write it as 1 minus r squared. This, you can say z is equal to r. So upper is the spherical part minus the lower, which is r, the conical part. And the thing that I have left over is the volume that I want, which is this ice cream cone here, but everything inside. Imagine packing the entire cone with ice cream, which I know they don't usually do. And then you have this piece of ice cream above it also. Times dA, which is r dr d theta. Okay, so there we go. Distribute the r, and I split it into 2. Oh, yeah, these are constants. These are constants. So this does qualify as just take out the theta. The length of the interval is 2 pi. Okay, there's no theta involved anywhere here. These are constants. These are constants. So just take out the length of the interval, which is 2 pi. Just integrate with respect to r. So if I distribute, I'll have r radical 1 minus r squared dr. I call that I1, first integral, minus the integral of r squared dr d theta. This one's fairly easy. So my integral is going to be 2 pi I1 minus I2. I call that I1 minus I2. Okay, so for I1, if I were to do a U substitution, U equals 1 minus R squared. Du is negative 2R dr. I put a negative 2 inside, negative a half. Okay. I'd be integrating radical U. But rather than doing all that stuff, just how do you integrate radical U? That's U to the half. So 1 minus R squared to the 3/2 times 2/3 from 0 to radical 2 over 2. Okay, this comes out to be negative 1/3. If you plug in 0, you don't get 0, you get 1. Okay, radical 2 over 2 squared is a half. And 1 minus a half is a half. So I have 1/2 to the 3/2 power. So I turn this around to make it positive 1/3. 1 minus 1/2 to the 3/2 is 1/2 times the square root of 1/2 radical 2 over 2. Clean it up. 1/3 times 4 minus radical 2 over 4. Common denominator is 4. 1 is 4 over 4. So 4 minus radical 2 over 4. That's I1. Okay, I2, that's easy. I'm integrating r squared. So r cubed over 3 from 0 to radical 2 over 2. Plug in 0, you get 0. So you have 1/3 radical 2 over 2 cubed, radical 2 cubed, radical 2 times radical 2 times radical 2, 2 radical 2. 2 cubed is 8. So cancel 2 with 4, radical 2 over 12. So finally, for my integral, I said that it was 2 pi I1 minus I2. So 2 pi I1 came up with this 4 minus radical 2 over 12. And then minus I2 radical 2 over 12. So 4 minus radical 2 minus radical 2. That's 4 minus 2 radical 2, 2 pi over 12. Factor out the 2, cancel. Pi over 3 times 2 minus radical 2. So finally, that's my answer. So that was definitely much more difficult. Okay, this fell under the category of upper minus lower, just like over here, upper minus lower. You integrate F minus G to get the area. So you integrate the upper, the sphere, minus the cone to get the volume. Okay, and the area that I'm integrating over is this circle, which is a circle center of the origin with a radius of radical 2 over 2. So that's the picture. All right, so that's how that one goes. Okay, I was just going to do a couple more, then I'm ready to start the next section. 29. Evaluate the iterated integral by converting the polar coordinates. Okay, it looks pretty bad in rectangular coordinates, so switch it to polar. Okay, yeah, I messed up again. Okay, e to the negative x squared minus y squared. Okay, we know that's e to the negative r squared. Okay, y goes from 0 to radical 4 minus x squared. Well, that's part of the circle x squared plus y squared equals 4. If you square both sides, do a little bit of algebra, move that over, it's x squared plus y squared equals 4. And x is going from 0 to 2. So this is the region. It's only the first quadrant part that I want. Okay. All right, so on this region, r is going from 0 to 2, theta is going from 0 to pi over 2. This would actually be quite messy in x and y, but in polar coordinates, it's very nice. E to the negative x squared minus y squared, that's e to the negative r squared. And then dy dx, that's dA, right? Which is now r dr d theta. So r dr d theta. And now that's fairly easy. Okay, that should be at 1/2 there. Okay, so again, use substitution. The derivative of negative r squared is negative 2r, negative 2 inside, negative 1/2 outside. Okay, this expression does not involve theta. These are constants. These are constants. So just take out the length of the interval, which is pi over 2. And there's a negative 1/2 outside. That would be e to the u, but you know the integral of e to the u is e to the u. So rather than writing it, we know it's e to the negative r squared. Can double check by differentiation. What's the derivative of e to the negative r squared? E to the negative r squared times negative 2r. So you know it works going from 0 to 2. Okay, so that's going to be negative pi over 4, but I can make it positive pi over 4 if I switch around the limits. Okay, that's usually preferable. So I plug in 0, I get 1. Plug in 2, I have e to the negative 4. So my answer is pi over 4 times 1 minus e to the negative 4. All right, then finally 31, and then I'm done with the section. Looks like this: xy squared dx dy. X goes from radical 3y to radical 1 minus y squared. That looks real bad. Y goes from 0 to half. Well, let's see what's happening. If x equals radical 3y, that means y equals 1 over radical 3x. The slope is 1 over radical 3. Like this. Okay, x equals radical 1 minus y squared. That's a unit circle, isn't it? X equals radical 1 minus y squared. Do some algebra. That's x squared plus y squared equals 1. So I'm on a unit circle. Y is a half. Now we know from trig, if the y coordinate is a half, on the unit circle, the x coordinate is radical 3 over 2. And what confirms it is, take a look at this. What happens when you plug in radical 3 over 2? The radical 3's cancel out and you have a half. So here's my picture. So x is going from the line to the circle, like so. So I have this piece of pie right here. So r is going from 0 to 1. Theta is going from 0 to, this would be 30 degrees or pi over 6. Okay, so my new integral, r goes from 0 to 1. Theta goes from 0 to pi over 6. Okay, x, r cosine theta. Y squared, r sine theta squared. And then dx dy is r dr d theta. And there we go. So I have a grand total of r to the 4th, r squared, r to the 4th, sine squared theta, cosine theta, dr d theta. Okay, so integrate with respect to r, that means theta is a constant. R to the 5th over 5, r goes from 0 to 1. Leave the sine squared theta, cosine theta alone. Plug in 0, you get 0. Plug in 1, you get 1/5. So 1/5 comes outside. Okay, now I'm integrating sine squared theta, cosine theta. So if I do a u substitution, that u equals sine of theta, here's the derivative, perfect, right? U equals cosine theta d theta. So I'd be integrating u squared. But instead of actually doing that, just leave it as sine. So sine cubed over 3. And yes, there's a 1/5 in front. Okay, again, if you're not convinced of that, ignore the 1/5. What's the derivative of sine cubed over 3? 3 comes down, knocks out the 1/3. You'd have sine squared theta, then by the chain root times the derivative of sine theta, which is cosine theta. There it is. It's perfect. Okay, this is going to be 1/15. Plug in 0, you get 0. Sine of pi over 6 is 1/2. 1/2 cubed is 1/8. So I have 1/15 times 1/8. Final answer is 1 over 120. And there we go. All right, so that is polar coordinates. I'm going to mark this off. Okay, and the quiz on Thursday, I'll give you a problem like this. So just be something involving 15.3 polar coordinates. Okay, so I'm going to start 15.4 today. So next time I'll do 15.4, 15.5, and then we'll take our quiz. And as you can see, there aren't that many problems here, but that doesn't mean this is short. Okay, 15.5 is actually not that bad. 15.4 can get really long. So I'll introduce that today. Okay, and yeah, let me do my focusing thing again, since I know whenever I put it down on the table, maybe you can't see it. So for those of you who can't see it, I'm raising this up so you can watch the video maybe. Hopefully it's a little bit easier to see. Okay, and then 15, stuff in the middle there. And then here. Oh, you don't need that because I messed up. So. So there's that. And well, I messed up there again. So here we go. I was just thinking out of curiosity. You know, we teachers don't get to see each other teach. You can tell me if you want to, but you don't have to. You're not going to gain points or lose points because of this. But I'm curious if you've ever had a teacher that made as many mistakes as I did. I remember even when I went to school, saying, "Man, this teacher always, has it perfectly right and everything's exactly correct, and not me. I mess up like crazy." So anyway, all right. So that's 15.3. So go 15.4. What is it about? Okay, what time is it? Almost 7:30. Okay, I'll do some of the problems and then probably call it a night. Some applications of double integrals on page 1016. Okay, most of these are physics related. Okay, I'm only going to do very few problems which involves something called moments and center of mass. We could spend a lot of time on this section, but we don't have to. Okay, in fact, the physics people told us, if you don't cover all of this, that's okay. We know that you're not physics teachers, you're math teachers. Okay, so we just know a little bit about it and we'll see. All right, so what do you want to know? Okay, page 1017, put this on your cheat sheet, number 3 and 4. Something called M sub x. That's the moment about the x-axis. M of x, you don't have to write this stuff. The summation, just go straight to this. Double integral over the region D of y, rho of xy dA. That funny looking P is actually the Greek letter rho, R-H-O. Have you ever seen rho before? We're going to see rho later also. So it's y, rho, R-H-O of xy dA. The moment about the y-axis is the same thing, except we put an x here. M sub y is a double integral of x, rho of xy dA. Okay, rho is a density function. Okay, and this has to do with center of mass. So like say, there's a certain point where if you hold up on this, on my pen, let's say, it perfectly balances theoretically. Okay, and furthermore, this is not necessarily a symmetrically placed object. In other words, it's not the same density everywhere. Maybe it's thicker here than here and here and here. So every point on this surface, okay, might have a different density. Okay. All right, so you want to put this on your cheat sheet. This pretty much summarizes it all. Page 1018. The coordinates x bar, y bar for the center of mass. So we say x bar, y bar, just put the line over it. That terminology is used in statistics also for you people who've had stats. Sometimes you see x bar. Okay, center of mass of a lamina. So what's a lamina? It's just some piece. Okay, it could be a piece of metal, but it could be any object. Okay, so don't worry about, what's this lamina stuff? It's a material. We're trying to find the center of mass. Okay, so x bar is m sub y over m, or 1 over m, double integral of x, rho of xy dA. Y bar is m sub x over m, which is 1 over m, double integral of y, rho of xy dA. They'll give these to us. Okay, and the mass is just a double integral of rho. Double integral over the region D of rho of xy dA. So for any one of these problems, you have to do 3 integrals. I should say 3 double integrals. So you have to figure out the mass, which is double integral of the function they give you. Then you have to figure out m sub y, which is double integral of x times rho, and then divided by the m. And then y bar is m sub x, which is double integral of y rho xy dA. So any one problem has 3 double integrals. So in other words, to do problem number, or any of these, okay, 4 problems, right? Any one problem is 3 integrals. I should say 3 double integrals. So number 3, you have to do 3 double integrals. Number 7, you have to do 3 double integrals. Number 9, you have to do 3 double. Okay, so it's not as short as you might think. So I said, okay, if I give you 10 problems, it's going to get really, really long. Okay, so I decided to cut it down to quote unquote only 4. And I'll show you what it looks like. So this has to do with center of mass and tendency to rotate in the X or Y direction. It's what's going on here. Okay. In case you're wondering about the M sub X, why is it Y? Well, if you're on the X axis, okay, distance away from the X axis is actually the Y, right? That's sometimes called the moment arm. And likewise, M sub Y, moment about the Y axis. So here's the Y axis, but the distance away would actually be X. That's the so-called moment arm. Okay, tendency to rotate in the X direction, tendency to rotate in the Y direction. Okay. Bottom line, you want everything here. Now, other stuff that's here, but I'll leave it to the physics people, and I know some of you are taking physics. Okay, moment of inertia. Okay, we're not going to do any moment of inertia. Okay, but you can see they have their formulas. Okay. And let's see, you have something called radius of gyration, which I won't talk about. And there's some applications to probability. You'd have to take an advanced upper division probability class in order to get that, I suppose. Okay. All right, so again, we quote unquote only have to do 4 problems, but they're long, don't worry. There's a lot to these. So what are we supposed to do again? I'll show you maybe a couple of them. That's about it. So 3, 7, 9, and 11. Okay, so for any one problem, we have to do 3 integrals, 3 double integrals. The double integral over the region, double integral of X times the region. And by the way, it's not as easy as just X times the answer you got over here, right? There's no such thing as a product rule or a quotient rule for integrals, you might recall, right? And then we have to figure out this thing, Y times the original rho. And then X bar is this answer divided by this. Y bar is this answer divided by this. So, you know, conceptually, it's not that hard. It's just very long to do all of these double integrals sometimes. All right, so maybe I'll try to do 2 of them, and then that's maybe about it. All right. All right, so let me try to show you question number 3. Find the mass and the center of mass of the lamina. The lamina is just a substance that occupies the region and has a given density function rho. All right, so for number 3, X is going from 1 to 3, Y is going from 1 to 4, a nice rectangle, but the density is not constant. The density is Ky squared. Okay, what's K? Some constant. So every point on this lamina, this rectangular piece, might have a different density. Okay. All right, so here we go. So rho of xy is ky squared. And we're going from 1, 3 to 1, 4. 1, 3 cross 1, 4. Okay, we say cross, this is not cross product. This means x goes from 1 to 3, y goes from 1 to 4. If I have another cross, then z goes from whatever to whatever. All right, so for the mass, I just integrate this directly. No big deal. So from 1 to 4, 1 to 3, ky squared. I put dx first and then dy because this does not involve any x. And neither of my limits involve any x. So I can just take the length of the interval. What's the length of the interval for x from 1 to 3? It's just 2. Believe me, you really want to do these shortcuts. You don't want to go, k x y squared and then plug in 3 and plug in 1. Use a shortcut. It saves you a lot of time. Okay, k is a constant. And the length of the interval for x is 2. So I'm just integrating 2k, integral from 1 to 4 of y squared dy. So it doesn't look too bad. So I have 2k y cubed over 3 from 1 to 4. Okay, take the 3 and make it join here. You're allowed to do that. So 2k over 3. Plug in 4. 4 cubed is 64. Plug in 1. 1 cubed is 1. So it's 63. 63 divided by 3 is 21 times 2, 42k. So that's the mass of the object, 42k. Right, so that is 1 double integral down and 2 to go. Okay. Now I need m sub x. For m sub x, you multiply by y. I know it sounds a little bit counterintuitive, but for m sub x, multiply the original by y. For m sub y, multiply the original by x. Right? See m sub y on the left side, multiply the original by x. And m sub x, multiply the original by y. Okay. You might not think it makes sense, but if you reason it out, it actually does make sense. If you can't make heads or tails of it, don't worry about it. Just do the problem. But again, it's because we're saying m sub y, the moment about the y-axis. So you want the distance away from the y-axis, that's considered x. Likewise, m sub x, distance away from the x-axis. So if I'm up here, the x-axis is down here, you're actually taking y. The moment arm, so-called, is y. Okay. All right, so what do I do for m sub x? I just do the same thing as I had here, except just put an extra y. So that makes it y cubed. All right, now this integral becomes the same. I take out, there's still no x there. So take out the 2, right? Length of the interval of x, and take out the k. Only I'm integrating y cubed, which makes sense. It's the same as what I had here, which is y squared, but I had to multiply by y. So integral of y cubed is y to the 4th over 4 from 1 to 4. Okay, 2k divided by 4 is k over 2. Plug in 4. 4 to the 4th is 256. Plug in 1, you get 1. 255k divided by 2 is m sub x. Okay, 2 down and 1 to go. M sub y. Same thing, integral from 1 to 4, integral from 1 to 3. But this time I multiply by x. So k x y squared dx dy. And this time, the thing that I'm integrating has x and y. So no quick shortcuts there, except take out the k. Right, so take out the k, integral of x y squared with respect to x, then y squared is a constant. That's going to be x squared over 2, right? So y squared x squared over 2 from 1 to 3 for x. Take out the 2, so I have k over 2. So plug in 3. 3 squared is 9. Plug in 1, you get 1. So this is 8, right? 8 times k over 2 is 4k. 4k integral from 1 to 4 of y squared dy. All right, so 4k y cubed over 3 from 1 to 4, and then I'm home free. Okay, put the 3 over here. I usually like to do that. Take it right here. So 4K over 3. Okay, plug in 4, 64. Minus plug in 1 is 1. 64 minus 1 is 63. 63 divided by 3 is 21. 21 times 4K, 84K. All right, so finally I'm ready for X bar, Y bar. So X bar is what I got from M sub Y and I divided by M. Y bar is M sub X divided by M. Okay. So X bar is M sub Y, which I just got was 84K. And then divided by the mass, which came out to be 42K, that's 2. And Y bar is M sub X, which came out to be this 255K over 2 divided by 42K. Okay. Have I shown you this rule, or have you heard of that? You can slide the 2 down with the 42. When you see a complex fraction like so, 255K divided by 2, you can just slide the 2 down with the 42. It's 84K. Or you could say divided by 2 is multiplying by 1/2, so put the 2 there. Okay, that reduces to 85 over 28. Okay, so bottom line, the mass is 42K. The center of mass is 2, 85 over 28, which is a little bit more than 3. Okay, so for this lamina, this piece of metal or material or whatever, okay, the center of mass is here. In case you're wondering, that's not the exact geographic center of this rectangle. Okay, because it's not uniform, as we can see over here. All right, so that was all just one problem. So you can see it takes a long time to do. All right, so I think I'll just show you one more and then maybe that's about it. Okay, so 3, 7, 9, and 11. You don't have to do 5. I was just indicating here, I started to do 5 and I saw that the algebra was getting really bad. So I decided I'm not going to give it to you. Okay. All right, so how about number 7? Let's see what's happening with number 7. So let me show that to you. Okay, where are we? Okay, let's see. D is bounded by y equals 1 minus x squared and y equals 0. Rho of xy is equal to ky. Okay, so this one's going to be harder because it's not a rectangular region. Okay, the advantage with number 3 was at least it was rectangular, right? X was going from 1 to 3, y is going from 1 to 4. I started to do 5. It's a nice problem, but the algebra got really bad. So I said, forget it. Okay, so try 7. Y equals 1 minus x squared. Well, we know what that looks like. Okay, and the density function is ky. Okay, so here's the function. Y equals 1 minus x squared bounded by y equals 0, which is the x-axis. So it looks like this, right? Negative 1, 0, 0, 1, 1, 0. How do you get that? Plug in 0, you get 1. Set y equal to 0, x is plus or minus 1, right? And rho of xy equals k times y. Okay, now, your first impression might be to say, well, if I'm integrating from negative 1 to 1, why don't I just go from 0 to 1 and double it? You can't necessarily do that when you have a non-homogeneous lamina. Okay, you don't have the same density on both sides. Okay, maybe you physics people had this. Did your physics professor ever do this? It showed you a wheel, right? And the professor said, I'm going to roll the wheel. So, okay, we know what the wheel is going to look like. It just goes like this. Okay, but it was actually going kind of weird like this. Okay, and then what the professor did was turned it around and saw that it wasn't uniform density, right? There was this block of a much heavier substance here, which caused it to kind of bounce funny. Okay, I mean, we're used to uniform things, right? Like when you see a wheel, okay, it's like that, and it kind of looked like it's all the same. But until the professor turned it around and you saw, okay, it's not uniform, right? It was heavier on this side and lighter on this side. So when it was rolling along, it bounced around in kind of funny fashion. Whereas you and I would normally think, okay, if it's just going to roll, it just does what every wheel does. Okay, but that's not the case. So since we don't have uniform density here, I can't necessarily make the assumption that I can just, go from 0 to 1 and double my answer. So I just keep it. All right, so let's see. Integral from -1 to 1 for x and 0 to 1 minus x squared for y of k times y dy. I forgot to put dx there. Okay, and in case you're wondering, you cannot just take this as constant because x is in my expression on the inside. Okay, so again, if you have only numbers, both the inside and outside, you can play that trick that I did over here, but not here, because after I integrate with respect to y, I'm going to have some x's. So I can't just simply say, take the length of the interval, which is 2, and go from there. All right, I can't take the k out. Integral of y dy is y squared over 2. Integrate from 0 to 1 minus x squared. When you plug in 0, you get 0. Take the 2 out. Okay, and when I plug in 1 minus x squared, I have 1 minus x squared squared. Okay. All right. Now it seems like I'm contradicting myself, but I'm not in just a second. But 1 minus x squared squared is x to the 4th minus 2x squared plus 1. This is an even function. How do you know it's even? If I replace x with negative x, I get the same thing, right? So because I do have an even function, I can play that game of symmetry. Okay, so even though you can't do it in general, which is true, you can do it in specific cases, and that's when you have an even function. Okay, so I made the exception to the exception, I suppose. Okay. So instead of integrating from -1 to 1, I can integrate from 0 to 1. And that makes it nice. I can take 2 out, and that'll cancel that 2. So I'll just have a k in front. Okay, square this, x to the 4th minus 2x squared plus 1. Okay, so that's going to be x to the 5th over 5 minus 2x cubed over 3 plus x from 0 to 1. There's a k in front. The 2's cancel out. Plug in 0, you get 0, so don't worry about it. Plug in 1, you have 1/5 minus 2/3 plus 1, which is very easy arithmetic. And of course, the arithmetic is so easy, I messed up. Okay, sometimes it's actually, it could almost be comical how many mistakes I make, but anyway. So 15, 15, 15, right? So 3 over 15 minus 10 over 15 plus 15 over 15. Okay, that's 18 minus 10, 8. So 8/15 k. What is that? That's the mass of this object, the lamina, so-called. All right, 1 double integral down, 2 to go. Okay, these are long, no question about it. All right, so m sub x, put an extra y. For m sub y, put an extra x. Okay, so the original that I did was ky, m sub x, ky squared. Everything else is the same. So take the k out, y cubed over 3 from 0 to 1 minus x squared. Take this out, plug in 0, you get 0. 1 minus x squared cubed. Okay. This is pretty bad. So I have to try to expand this. Okay, However, it is even. Right? If I replace x by negative x, I get the same thing. So I'm going to play the same game of integrating from 0 to 1 and put a 2. Okay, 1 minus x squared cubed. I'm going to use Pascal's triangle. Remember doing that? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. My coefficients are 1, 3, 3, and 1, where that's like my A, that's my B. So my coefficients are 1, 3, 3, and 1. I'm going to have 1 cubed, 1 squared, 1, and nothing. Negative x squared to the 0, 1, 2, and 3. Okay, so I'm using the shortcut to save time. If you don't like what I did, just go ahead and cube that. Just go 1 minus x squared times 1 minus x squared times 1 minus x squared. But a shortcut is from Pascal's triangle, the coefficients are 1, 3, 3, and 1. You go 1 to the third, 1 squared, 1 to the 1, and 1 to the 0. They're all 1. And then this will be negative x squared to the 0, 1, 2, and 3. Okay. Maybe if I can sneak this in here. I'm not sure if I have space. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay. So the coefficients are 1, 3, 3, 1. A starts at the top, A is 3, and you go a squared, a to the 1, a to the 0. And b goes the reverse, b to the 0, b to the 1, 2, and 3. Okay. So anyway, it ends up being like this. So for the ones, it goes 1 cubed, 1 squared, 1 to the 1, and 1 to the 0, but those are all 1. And negative x squared to the 0, which means don't write it, to the 1, 2, and 3. And the coefficients are 1, 3, 3, and 1. Anyway, you clean it up, this becomes 1 minus 3x squared plus 3x to the 4th minus x to the 6th. Okay, and yeah, let me check the chat because maybe I messed up again. So what was that? Pascal's triangle, yes. Pascal's triangle. Yeah, so these give you the coefficients from Pascal's triangle. If you have absolutely no idea what I said about Pascal's triangle, you still have a way of doing this, right? You have to go 1 minus x squared times 1 minus x squared times 1 minus x squared and take my word for it. You end up with this. Actually, maybe you shouldn't take my word for it because I mess up so much, but it comes out to be this, hopefully. Well, when I did it, I checked the back of the book and it actually worked. So anyway, okay, so 2/3 k x minus x cubed plus 3x to the 5th over 5 minus x to the 7th over 7 from 0 to 1. Okay, plug in 0, you get 0, forget about it. Plug in 1, 1 minus 1, good, forget about it. 3 over 5 minus 1 over 7. So 2k over 3, common denominator is 35. Multiply this by 7 over 7, 21. Multiply this by 5 over 5, 5. So 21 minus 5 is 16. So 32k over 105. All right. M sub y actually comes out to be nicer, and I'll try to show you why. Okay, so same thing, integral from negative 1 to 1, 0 to 1 minus x squared of k x y dy dx. I decided to go dy dx this time. You can go either dx dy or dy dx, but I did it for this reason. So again, take the original. Where was my original? It was ky, wasn't it? Yeah, and to find m sub y, you put in an extra x. Okay, so k, take out the k, integral of y, x is constant, so leave the x alone, y squared over 2 from 0 to 1 minus x squared. Okay, so plug in 0, you get 0. Plug in 1 minus x squared. I have 1 minus x squared squared times x. Okay, this is going to be an odd function. Okay, you're gonna have odd exponents. If you don't believe me, well, maybe I should have written it out. This is x times 1 minus what? 2x squared plus x to the 4th. If I multiply it out, I'll have an x cubed, and an x to the 5th. I mean, that's the very definition of an odd function. If you ever integrate an odd function from -1 to 1, you automatically get 0. You don't even have to bother. Okay, so one more time. If you have an odd function, okay, if I square this, I have 1 minus 2x squared plus x to the 4th. Multiplied by x, it's x minus 2x cubed plus x to the 5th. All the exponents are odd. It's an odd function. Odd function means symmetry with respect to the origin. Okay. Maybe I'll sneak in an example here, like y equals x cubed is an odd function, right? Y equals x cubed. So because of symmetry, if I integrate from -2 to 2 or -3 to 3 or negative b to b, it's automatically 0, right? That's nice. So m sub y is 0. Now, if you're still not convinced, okay, this will be x, right? What's the integral of x? X squared over 2 becomes even. So you get the same thing when you plug in 1 or -1. See, that would be -2x cubed. So -2, x to the 4th over 4. Same thing when you plug in 1 and -1. They're going to cancel out. If you multiply these out, that'll be x to the 5th. When you integrate x to the 6 over 6. Same thing when you plug in 1 and -1. So it's going to be 0. Okay. So we're all set. So x bar is 0. It's m sub y divided by the mass, but m sub y is 0. So x bar is 0. So it does turn out in this particular case that the average x is right in the middle, right here. And y bar is m sub x divided by m. So that was this 32 over 105k, this strange thing over here, and divided by 8/15 k. K's cross out. So it's 32 over 105 times 15 over 8, comes out to be 4/7. All right, so final answer, x bar, y bar is 0, 4/7. So you can see there's definitely a lot to this. All right, so I showed you 2 out of them, and I was done, folks. It's almost 8 o'clock. Let me do my focusing thing again for you. So you can see, to do any one of these problems can get really long. And while I'm showing you this, hopefully focus, it was only with the shortcuts that I shared with you. If I didn't do those shortcuts, it would even be longer. I did the shortcuts of showing what happens when you had an even function and an odd function, right? Oh, you don't need to see number 5. Actually, number 5, I didn't mess up this time for a change. It was just getting to be too long. So here's 7. This shows you what happens if you try to integrate an odd function from -b to b. It's always 0. And using the shortcut of Pascal's triangle here. Otherwise, it can get really, really long. And there we go, folks. Okay, so if you have any questions, you can put it in the chat or unmute yourself. But otherwise, I'm done. So next time, I was going to maybe do one more 15.4 and then aim for 15.5. That should not be that bad. There's not that many problems. And these problems actually aren't that bad, believe it or not. It involves surface area. Okay. So everything goes according to plan. We would be up to here, 15.4, 15.5. So I'll do one more problem from 15.4, then we'll do 15.5, and then after the break, I'll give you a quiz, and then we're off a week, and everybody have a nice spring break, and we come back here. So again, we're not really that far ahead. Again, if pushing everything back, I'm really only one day ahead, it looks like. We can easily be lost if I get sick or my internet goes down, or something like that. But as it stands, it looks like I'm a day ahead. from here, because this was the original schedule where I thought the final exam was here. So I think after Thursday, we'll just be one day ahead, and then we're off for spring break. Okay, so that's that. Anybody have any questions, please? Otherwise, we're going to call it a night. You can either unmute yourself or put it in the chat. All right, I don't hear anything and I don't see anything, so we'll call it a night. All right, so I'll do this. The quiz will only be on polar coordinates 15.3. I'll just give you a polar coordinate problem and that'll be it. Okay. All right, that's it for tonight, folks. Everybody have a good night and we'll see you next time. Okay. All right, good night, everybody.
Bye.